Okay, so welcome back to another week. We're going to be going through chapters 7 through 10 this week, which will be focused on the solar system. And so today, in this lecture, we'll first start with a sort of an overview, and then we'll get into some of the details, primarily focusing on the inner solar system. And then next week, we'll continue on to the outer solar system. So, okay, first for chapter 7 with an overview. So where does this all begin? Well, we know from ancient times, as we've discussed, that people were able to identify the planets as sources of light that didn't follow the same pattern as everything else. So remember, planet means wandering star in Greek, and so planets were the objects that ancient astronomers saw moving across the sky relative to the stars, which of course would rotate, and we would see them at differently at different times of the year, but the planets would move relative to those constellations. And so it wasn't until the era of the telescope, so Galileo's time and after, where humans were really able to gain much more information about the planets. And so Galileo, if you remember, he was able to see in the early 1600s the moons of Jupiter, as well as things like the rings of Saturn and some other features of the solar system that really opened people's imagination and basically started us down this road of astrophysics, applying the laws of physics, understanding that the things in the solar system are objects that follow the same laws as things down here on Earth and can be made of the same substance. They're not anything mysterious or ethereal. But it took a while longer for telescopes to get good enough to start to really understand the planets in more detail. So the moon, of course, we could understand and we could see, have what we now know as our craters and sort of lava fields and all these weird features. It took until the 1890s for telescopes to get good enough to start to see similar features on Mars, which really created a spark of imagination in people at the time and led to a bunch of really good novels and science fiction. But in order to really understand the planets and to see them better, we had to actually send things out to them. And we've only been able to do that in the last 60 years or so. So we really live in this era of exploring our solar system. We're finally able to do it. We haven't really gotten much outside of our solar system, but we've managed, starting in 1957 with the Soviet Sputnik project, where they were able to send a probe into Earth's orbit. And then pretty soon after, the Venera 1, which was supposed to hit Venus, but missed a little bit and flew past. This is it down in the bottom. It looks really wacky. So that was all the way back in 1961. So that was kind of the beginning of this era of exploration where we've really started to gain a lot of insight in terms of what the planets are made of, what they look like, how they're all unique and different little creatures, basically, but they also have some similarities. Okay, so let's do a quick inventory by mass. So I think most people don't necessarily appreciate this fact if they're not astronomers, but almost all of the stuff of the solar system is within the sun. So as we can see here, the sun is 99.8% of the mass of the solar system. Really incredible. Next up is Jupiter, which is 0.1%. So 1 in 1,000 of the particles in the solar system are in Jupiter. We're going to talk about this more later, but if Jupiter had actually grown larger in the early solar system, it would have turned into another star, and we would have had 2 stars in our solar system instead of 1. That's actually pretty common, probably more common in the universe to have 2 stars than just 1. And then as we can see, the rest of the solar system is somewhere split between the planets, the moons, the comets, the asteroids, and some cosmic dust. But you can see it's all fairly minuscule in comparison to the star of the show, which is the sun. Okay, so what about the layout of the solar system? Well, we all know that the solar system is a bunch of planets and things orbiting the sun. So this picture, the blue orbits, those are the planets. And so what we can see is that the planets are on a pretty flat plane. So almost all of them, from our perspective, they're on the ecliptic plane, or very close to it, very similar to how we see the sun travel across the sky. So when we see the sun, its position, and the moon, its position, the rest of the planets they tend to be along that same line. Now, some of them might be obscured by the horizon at any given time. When we go farther out and when we look at smaller objects in the solar system, they can have much more wacky orbits. So we can see Pluto in the upper right here. Pluto, which we now consider a dwarf planet, which we'll talk about more later, has a pretty tilted orbit. It's not really on the ecliptic so much as the rest of the solar system, or the inner solar system. And when we start to get out to things like comets, it really becomes more spherical. So the solar system, the main part of it is a disk. It's pretty flat, like a record. But the larger, as we go farther out, the larger solar system is much more spherical. Okay, it's just the region of space that feels gravity of the sun stronger than of other stars. And it extends pretty far out. We're going to see this a little later, but the outer edge of the solar system, where the sun's gravity stops being sort of primary, isn't for a light year or so. So it's pretty big. Okay, so then what about these inner planets, the terrestrial planets? So the four inner ones, Mercury, Venus, Earth, and Mars, shown here, going around counterclockwise. We call them terrestrial planets because they're mostly made of rock and metal. Sometimes when we talk about terrestrial objects, we also include Earth's moon, which is very big, and it's also in the inner solar system, and it shares a lot of similar properties in terms of composition. And so the solid surfaces of these planets mean that we can actually see like craters if things have impacted with them in the past. And it also means we can send little robots and things and land on them. Starting with Venus and Mars, and I mean, obviously we live on Earth, we've been able to send experiments to the surface of these planets to understand what they're made of, to get samples of them, and to better understand where they came from. Moving out farther, we get to the gas giant planets. So as you can see, these are much bigger. This is a roughly to scale picture here. And the gas giant planets, as an astronomer, the giant part is very reasonable. They are quite big. The gas part we have to be careful with. So the inner core of these planets is where the heavy stuff sinks to, and that's rocks and ice and metal. Surrounding that, it's actually kind of complicated. It's a gas liquid. It's a very weird state of matter due to the high pressure, right? All the weight of the planet is squishing down, basically compressing this gas until it's something a little bit different than how we think about gas here on Earth. It becomes much more similar to a liquid like water, but with some very strange properties. So these planets are held together by gravity. And basically, because they're made of a fluid, whenever something hits them, we can see it temporarily. There'll be a little dust cloud or gas cloud, but it quickly vanishes. Basically, all of the rotation of the planet causes these fluids to constantly mix and obscure any history. So it's harder to study them for this reason. Okay, so we often use these sort of data tables, and you'll encounter many of them. I'll ask you to get information from them yourselves. But these help us to understand what the solar system looks like quantitatively, numerically. And so we can see in this table that we have all the planets, they're in orbit. They're in order based on their orbits. And we have the distance from the sun in this first column here. So Mercury is 0.39 AU. Remember, an AU is just defined as the distance from the Earth to the sun. So, of course, 1 AU for the Earth. And we see by the time we're at Neptune, we're at about 30 AU. Now, of course, planetary orbits are not circles, they're ellipses. So these are just average distances. It varies a little bit throughout the orbit because the sun is at the focus point, not the center. and the orbits are not circular. We also have the period. Remember, this is related to Kepler's third law, that t squared is related to a cubed. So these two, the distance and the period, are related. And we see that every planet has its own year, which is how long it takes to orbit the sun. Of course, on Earth, it's equivalent to 1 Earth year. And we can measure all the other planets' years relative to Earth's years. So we see Saturn takes about 29 Earth years for it to have 1 Saturn year, for it to revolve around the sun. We also have the diameter and mass, and if we put those together, if we calculate the volume basically and do mass over volume, we can get the density. And the density, remember, tells us basically how heavy a given quantity of this substance is. And what you'll notice is probably not a surprise, but basically the inner 4 planets, Mercury through Mars, have a pretty high density, around 4 to 5. And the outer planets have a much lower density, around 1. 1 is actually the density of water, so anything less than 1 would float in water, and we actually see that Saturn has a density less than 1. It's 0.7. So if you could find a big enough bathtub, it's a fun fact that Saturn would be able to float in it. And so this is what it means to be a gas or a liquid sort of fluid planet, these outer giants. Okay, what else is in the solar system? Well, we have many smaller members. So in addition to the sun and the planets, we have comets, which are sort of icy dust balls that have really crazy eccentric orbits. So we tend to only see them every few decades, if that. We also have asteroids, which are smaller rocks that were sort of didn't end up being part of any of the planets. So they're just kind of floating around from the early days of the solar system. And then the even smaller rocks, we call that cosmic dust. So things that aren't big enough to be an asteroid. And most of those are what actually end up becoming what we call meteors. So a meteor is just anything that's burning up in Earth's atmosphere. We can see it traveling very quickly across the sky. Many meteors, like many hundreds of reasonably sized ones, hit Earth's atmosphere every day. But only a few, which are the biggest ones, are large enough that they don't completely get burnt up as they travel through the atmosphere. And the ones that manage to hit the ground, we call those meteorites. So those are what you probably think about when you think of these impacts. Those are the meteorites. Okay, so we've seen the rough sketches of the solar system, but what does it look like if we want to draw it to scale? Well, it's really hard to do because the scale, like most things in astronomy of the solar system, is pretty crazy. So this picture is roughly to scale, and we can see that Mercury, Venus, Earth, and Mars are all really close to the sun, right? Mars is only 1.5 AU, and then in between Mars and Jupiter, you may know there's a big belt of asteroids that were left over from that formation of the solar system. And then, so you see Jupiter is quite a bit farther away, and the remaining gas giants are spaced farther and farther apart as we go outward. And so remember here, 1 AU is 150 million kilometers, like we list here. So these are really crazy distances. And not only that, but you see how it gets progressively more stretched out as we go farther and farther. We can also see just how large the sun is as part of this picture. So the sun is truly massive. And as we talked about, it's over 99% of the mass of the solar system is in the sun. And so just as a shout out, at Saddleback in the Science Building, we actually have a scale model set up of the solar system. So you can walk around and actually appreciate these distances involved that way. So what if we want to compare the sizes of the planets? Well, this is a picture if we actually do that properly. So on the left are the terrestrial planets. So Mercury, Venus, Earth, and Mars. You see Venus and Earth are very similarly sized. Then we have Jupiter next to it, much, much larger. And then the sun doesn't even fit in the picture, right? Remember, we could fit 1 million Earths into the volume of the sun. It's just really that massive. Okay, so what about the names of all of these objects? This is worth talking about for a moment. So obviously, in every language, every culture, people have known about the planets for a long time. So they have names in every language and culture where people have done astronomy in the past. In the modern era, basically because of European colonization and because of English becoming a kind of a lingua franca of global science, we tend to use the English names internationally, especially when we're doing astronomy. And so the planets in English, their names come mostly from Greek and Roman mythology. And actually, when Herschel discovered Uranus, he wanted to call it Georgium Sidus, which is George's star after King George the Third. And people were really not happy with this. There was a lot of pushback. And so this is how we ended up eventually going back to Uranus, which is another sort of Greco-Roman name. And that's stuck ever since. So for larger objects, especially within the solar system, we tend to use Greco-Roman mythological names. More recently, they've been branching out and trying to use other mythologies. When it comes to features like craters and mountain ranges on planets and asteroids and all sorts of other things, the names get a lot more wacky. So there are some conventions that people have developed. So, for example, on Venus, all of the different features are named after famous women, like in science and other pursuits. I know there's some moon, I want to say, of Jupiter, where all the features are named after characters in Shakespearean plays. So a lot of these sorts of things, cultural references. Asteroids and comets tend to be named whatever people want because there are so many of them. So a lot of comets especially are named after whoever discovers them, like Halley's Comet. Who's in charge of all this? Well, that's where the IAU, the International Astronomical Union, comes into play. So the IAU is a big organization that basically has scientists, astronomers from all over the world, and they can vote on these different naming conventions and basically create a standard for everyone to agree so that we can, get to doing more interesting science and not be fighting over names as working astronomers. We want to be focused on the actual interesting physics and things. And you can actually go on their website and see all of these naming conventions. They have this huge wiki page, which I took a screenshot of here, just to give you a sense of how much work goes into this process of naming. Okay, so now let's dive into the composition a little bit more closely. So people who aren't astronomers don't tend to appreciate that Jupiter and Saturn and Uranus and Neptune are quite different from one another. So Jupiter and Saturn are pretty similar. They're relatively close together. And because they're a little bit closer to the sun, they're made primarily of hydrogen and helium, basically the same elements that were formed in the early universe. The core of these planets is rock and ice and metal, so that's just due to things colliding with them and sinking to the middle. But the rest of it is really mostly hydrogen and helium. Now, hydrogen and helium on Earth are gases, and that's one of the reasons we call these gas giants. But under the crushing weight of gravity in these huge planets, these elements become weird states of matter, like I was talking about earlier, where they're kind of like gases and liquids mixed together in a weird sort of behavior. Now, Uranus and Neptune are quite different. So they're farther out in the solar system and relatively near to each other. And so they actually are only about 15% hydrogen and helium. Most of their mass, 60%, comes from different ices. And when I say ices here, again, it's under so much pressure that they behave differently from ice here on Earth. But a lot of it really is water ice, which is kind of crazy. Water ice is actually pretty common in the solar system, believe it or not. But there are also other compounds and elements, so things like ammonia, which is what's in Windex, right, cleaning agents. Methane, which is like a gas that you can burn for heat. So these sorts of things, but instead of gases, they're liquefied or icified, and they become these weird like superionic fluids, and they can become conductive. They can like exhibit different crystalline structures. So all sorts of weird properties due to the really high pressure environment when you're being crushed by the weight of a planet on top of you. But they still do flow, and so they still have this ability to obscure any impacts, any collisions, as those fluids move around due to the rotation of the planets. Okay, what about the terrestrial planets? Well, the inner four planets are much more rocky, so comprised of rock and metal. Of course, the Earth also has quite a bit of liquid water on it. But if you think about the volume of the Earth, most of it is made out of different rocks and metals. Metals tend to be denser than rocks. And so the planets with the higher densities, like Mercury, tend to have more metal. Whereas things like our moon with a lower density, that tells us it has less metal and more rock. Rocks are mostly made of silicates, which are silicon and oxygen. And you can see this is Earth's crust composition, is mostly oxygen and silicon. So it's kind of weird. We don't think of Earth as being made of gas, but in a way it is. You know, rocks are just gas that has bonded in such a way that it becomes solid. That's what it means to create minerals. Now, the metals in Earth are really varied, but the majority is aluminum and iron. These are really rare in the universe, but due to the way the solar system formed, they're pretty common in these terrestrial planets. And then we'll talk about this more later, but differentiation is something that we see in the terrestrial planets and affects their composition. This is basically the process whereby when a planet heats up enough that all of the rock melts, so similar to the magma in Earth today, the heavier things will then sink towards the center and the lighter things will be left on the surface. So this happened to Earth, for example, and this is why a lot of the iron on Earth is actually trapped in the core. The core of Earth is primarily made of iron, whereas a lot of the surface has more of these silicates, which are lighter, relatively light rocks. Okay. So then what about the composition of the rest of the solar system? Well, moons, their composition really depends on their location. So Luna, or our moon on Earth, is very similar in composition to Earth, but with less metal. And it was also differentiated in the past, even though it's all solidified now. Outer moons, so like Jupiter's moons, tend to be less differentiated, so maybe they never heated up enough to melt. And they also have more ice buildup. So a lot of moons, you may have heard of Europa, which is covered in a liquid water ocean with a thick layer of ice on top of it. We'll definitely talk more about it later. Asteroids are really interesting. They tend to have much higher metal content, depending on where they were formed. And so you may have heard people talk about asteroid mining. So there are lots of metals that are very rare on Earth, but certain asteroids have in abundance. And so if we could send a spaceship up there and grab them, it could potentially be very beneficial. Of course, it's expensive to make spaceships, especially big ones, to carry rocks back and forth. So probably not something that'll happen really soon, but eventually, definitely, possible. And then comets tend to be much more ice heavy. So not just water ice, but also these other ices like ammonias and methanes and similar sort of compounds. Okay, so what about temperature? Well, the sun is like the campfire of our solar system. So generally, the closer you are to the sun, the hotter you're going to be. So for example, Mercury is very close to the sun, so it's very hot. What you'll notice in this chart, though, is that it is not the hottest planet. Venus is actually even hotter. This is due to Venus having an atmosphere of gas that acts like a blanket due to the greenhouse effect. It traps heat on the surface and causes Venus's surface temperature to tend to be higher. But ignoring the effects of atmospheres, generally temperature goes like the square root of distance. So for example, Pluto is 100 times farther away from the sun than Mercury. So if we take the square root of 100, that would be 10, right? 10 times 10 is 100. And so Pluto is about 10 times colder than Mercury. Okay, and so then in addition to the sun, we can also sometimes get heating due to tides. This isn't really common for planets, but for moons, especially the moons of Jupiter and Saturn, this is what allows moons like Europa to still have a liquid ocean and moons like Io to have volcanoes. Not due to the sun, but due to the sort of squishing, compressing due to this difference in gravity that causes the tides. Okay, so speaking of volcanoes, so geological activity, this is when a planet or a moon has some, magma, right? Some molten interior left over that allows for volcanoes to form, for plate tectonics to happen, basically to reshape the surface of the planet in some really complicated ways that, from our perspective as astronomers are often annoying because they obscure the history, which we're interested in learning about, of the planet. And so Earth and Venus are the most geologically active planets. They both have plenty of volcanoes and some plate tectonics, all sorts of things like this. Mars, we can tell, used to have these effects, but because it's cooled down, it's a smaller planet, so it's cooled more quickly. It doesn't have much geological activity today. And the moon is, like our moon, is an even more extreme example. It's much smaller than Mars, and so it cooled long ago, even though it used to be molten. And so as a result, it is geologically dead. No new mountains are forming on the moon. No volcanoes happen on the moon. It's just a big ball of solid rock as far as we can tell. Okay, so on that note, you might wonder, how can we date a planet? And basically, when we have a terrestrial planet, our job is a lot easier because we have a surface. So the surface of the terrestrial planet, it had to have solidified at a certain time, and we can try to figure out when that time is, basically by looking at two different mechanisms that we're about to talk about. But before that, I want to highlight that with gas giant planets, this is much, much harder, and we basically have to use like fluid dynamic simulation, and we have to maybe model the progression of the solar system or use other really complicated methods, indirect methods, to try to figure out their age, because the surface is just a big swirly ball of liquid and gas. However, terrestrial planets are not super easy because they can also have things like atmospheres and that geological activity we mentioned, which can reshape the crust and make it harder to figure out how old the planet is. Okay, so one way, going to these two methods that we have for terrestrial planets, one way is by counting the number of craters. So basically, the longer a surface of a planet has existed, the more craters there should be, because there's been more time for meteors to come and hit the planet. Okay. But in general, we have to be a lot more careful than just saying more craters equals older. This is because bigger objects and heavier objects tend to attract more dust and asteroids and comets, and they tend to then have more craters. So the size and weight of a planet will also affect this. And then, like we talked about, if we have rain or wind or volcanoes, those can cover up the effects of craters and cause us to underestimate the age, because we don't see as many as we might have had those effects not existed. And just as a fun comparison, I wanted to show you, so these are pictures of the moon. So as we talked about a few weeks ago, the near side of the moon is what we all see from Earth, whereas the far side always points the other way. This is because the moon rotates around its axis as it rotates around the Earth, and those happen to happen at the same speed due to some physics we'll discuss later. It's called tidal locking. And so as a result, we only ever see one side of the moon. And that actually means that the side we see has fewer things hit it because the Earth is kind of in the way of many things that might hit it. Whereas we can see the far side has more craters, more impacts, because it's facing outward, has more opportunity for something to collide with it. That's just another complication we might have when it comes to counting craters to estimate age. Just as a quick note, the black spots on the near side of the moon, those aren't craters, those are ancient lava fields. So we'll talk much more about those later, but I just don't want you to get confused with your counting, including those. Okay, what about the second method then? Well, the second method is using radioactive rocks. So, okay, we talked about radiation last week. That was thinking about electromagnetic radiation. This is a little bit different than that. So electromagnetic radiation, those are just different forms of light, like radio waves, visible light, X-rays, UV, all these things. Radiation, when it comes to rocks, this is probably closer to what you thought about before this class, right? Like a glowing green rock that causes cancer, this sort of thing. Some of these rocks do emit electromagnetic radiation, but a lot of them emit other particles like protons or neutrons or electrons, these sorts of things. And they emit them with a lot of energy. And when they do that, the atom itself actually changes. Maybe it breaks apart, maybe it mutates into another atom. And we call that radioactive decay. And basically each element or each isotope has a different rate, a different speed that it decays at. We have a little table here of some examples. So for example, uranium-238, it'll decay into lead-206, and it has a half-life of about 4.5 billion years, a very, very long time. That's about the age of the Earth, roughly. And so how do we use this? Well, if we know the half-life of the element, which we can measure in a laboratory, and we know how much of the element existed long ago, then we can measure how much there is now, and we can figure out how much time has passed. So this is what we mean by radioactive dating. We can do that on Earth to figure out how old fossils of dinosaurs are, things like this. We can also do it for rocks from planets or asteroids or other things. We just need to get a sample of the rock, have a method to estimate the starting composition, and then use half-lives to figure out how old it is. Some people get confused by half-lives. The idea just comes from probability. Basically, each atom has some probability to decay. And so if we take a bunch of atoms, after a certain amount of time, half of them will have decayed, and the other half will have stayed the same. If we take the half that stayed the same, we can wait that same amount of time, and again, half will have decayed and half will stay the same. So we can do that over and over and over again. Each time we're left with a half, and then so half of a half is a fourth, half of that is an eighth, and that's what this chart is trying to represent here. Basically, after each half-life, we're left with half of what we had before. So half, a fourth, an eighth, a 16th, it just keeps going smaller and smaller. And so using this kind of math, we're able to estimate the age of any rock that happens to have some element like this in it. So that's our second method. But like I said, these are really only useful when we have a surface, like a terrestrial planet, that we can date. If it's a gas giant, it's much, much trickier. We'll maybe talk about that a little bit more next week when we get to the outer solar system. Okay, so with all this background, we can start thinking more critically about the bigger questions. Where did our solar system come from? And basically, we can start to do astrophysics. We can use the laws of physics and what we observe today to try to rewind the clock and figure out what the solar system looked like in the past. So we have two big clues that we can use. One is that the solar system, the inner part, the 8 planets, is pretty flat, right? It's all in this ecliptic plane. And so what that means is basically what the laws of physics require for that to happen is that there had to have been lots of collisions between all of the stuff that made up the solar system. So if you imagine, you have a big ball of stuff that's all colliding. Over time, it will average out and it will cause whatever the net rotation direction is to be the flattened orientation of the solar system. So I'll try to find a video maybe of this so you can see this in action. But it's really magical. As the things collide, all of their motion will cancel out and we're just left with rotation in one direction. And so this is, in physics, we call this the conservation of angular momentum. And in order for that to happen, we have to have a solar system that starts as what we call a solar nebula. It has to be a very dense sort of ball of gas and rock that gets hot enough and has enough energy that things are colliding so that this process of flattening can occur. Now you notice we talked earlier about how the outer solar system is more spherical. That's because that part of the solar system didn't have these collisions. There wasn't enough activity out there. Things were more spread apart. So it's retained that spherical shape that it would have had when it formed. In addition to the flatness, we can also look at the composition of the solar system. It's pretty similar throughout, except the terrestrial planets don't have much hydrogen and helium. So you might wonder, where did it go? And basically, what the physics tells us is that as the sun heated up, which we'll talk about how that happens again later in another chapter. So as the sun heated up, it kind of blasted this gas away from the inner solar system. So it used to be there, it got blasted away, and then it got absorbed by Jupiter and Saturn. That's part of why they have so much relative to the rest of the solar system. Okay, so how else can we understand our solar system? Well, we can look at other solar systems, other solar nebulas out in space. And the beauty of doing this is we can see snapshots. These are some examples of these solar nebulas, these forming solar systems at different moments in time. Remember, light takes time to travel. So if we look at solar nebulas that are really far away, what we're seeing is a snapshot from when they were really young, long ago in the early universe. And so this is really, really helpful because it's like having a bunch of examples that we can compare to in order to make sure that our physics and our simulations, our models are accurate. And this has been how we've been able to really develop a thorough understanding of our solar system. And so in doing this, we've created a catalog of all sorts of solar nebulas that we can compare at each moment in their evolution to understand how our solar system formed. And in order to do this, we need some really powerful computers. So this is a picture of a server room with a supercomputer. And so using these powerful computers, we can actually do the physics. We can say, let's start with a solar nebula, a big sphere where we have a bunch of little rocks and dust and gas. And then we can apply the laws of physics. So they start to pull on each other. They start to get closer. They collide. As they do this, right, the solar system, that nebula flattens. We call it a circumstellar disk. So circum means around, like circumference. So around a star, and it's a disk. So that's, as the solar nebula flattens, it becomes a circumstellar disk. And in that process, clumps start to form, which we call planetesimals, so small planets, right? And as they collide, sometimes they clump together, sometimes they split apart. And all of these collisions, and as well as the radioactive elements inside of them, cause them to start to heat up until they liquefy. And that's when we get differentiation. So as they glob together, the heavier parts go to the center, the lighter parts go to the outside. And so this was a really violent process. So nowadays, the solar system is pretty calm. All the planets are on their own orbits. They don't bother each other. Only the occasional meteor or asteroid causes a problem. But in the past, the solar system was really, really violent. We needed that violence to flatten out the solar system and to cause these planets to get big enough that they look the way they do today. And so we can still see some of the clues of this past violence. We can see it in the fact that the moon has a very similar composition to Earth. We'll talk about why that is a little later. We see it in how Uranus and Pluto actually spin on their sides. That's really wacky, but you can imagine if something hit them really hard, we could cause that to occur. And we also see it in how Venus actually spins backwards. It rotates around its axis the wrong way, also likely due to some of these violent collisions in the early universe. And so we can simulate all of this. We can build a computer where we have these masses and we allow them to crash into each other in our computer following the laws of physics, right? Similar to a video game that has laws of physics coded into it. And we can actually see the solar system evolving over time, and we can get a lot of really useful insight. And we can also compare it to these other solar nebulas and circumstellar disks we see throughout the universe. And we see them at different stages in their development. So we have a lot of data, we have a lot of tools, and this is why we've been able to get such a good and deep understanding of the history of our own solar system through this process. Okay, so that's where we'll leave off for chapter 7, and we'll start chapter 8 in the next video. So I'll see you there.